I am Dr. B.L. MATHUR, Professor of Electrical Engineering, Jeets Institute of Technology, Jodhpur. Today I am going to take the topic elements of circuit breakers. Switches are used to switch on or to switch off current in an electric circuit. When the voltages and currents to be handled by the circuit like a power system is very high, of the order of kilovolts and of the order of kiloamperes, then the switches are of very special design. So circuit breaker comes in that category for high voltage and high current switches. Now a circuit breaker can be explained in three parts. One is an isolator, a load break switch, and third is what we call a circuit breaker. While making a circuit is not much troublesome, because while making a circuit the current will rise quickly from a low value to a high value, and metallic part of the switch should be strong enough to withstand the electromagnetic forces during switching. But while switching off, there is a arc produced between the contacts, and quenching this arc is the biggest problem while switching off. Now, isolators are the switches to handle low current like that at no load currents. It can also handle small magnetizing currents of transformers. It can also handle the capacitive currents of line at no load. The load breaking switches can switch on and switch off up to full load current in the circuit. And circuit breakers can be switched on and also switched off at faults. So when short circuit is there, even then at that time we can switch on and switch off a circuit breaker. A circuit breaker is not damaged due to switching on or switching off at fault level. So rating of circuit breakers are so designed as to switch on and switch off fault currents. We will confine our discussion only to the study of circuit breaking in circuit breakers. That is, during fault current, if a circuit breaker is switched off, how the circuit breaker behaves and how should we design it so that it can successfully perform its duty of bringing down the current in the circuit to zero. Now, in a circuit breaker, there is a fixed contact and there is a moving contact. The moving contact is pressed against the fixed contact under a spring force, and then it is locked. When a circuit breaker is required to operate, then the lock is pulled out. So violently under the string force, the moving contact moves away from the fixed contact and a gap is created in the circuit, and that ultimately switch off the circuit breaker. In order to keep the contact resistance during the closed period of the circuit breaker, the fixed and moving contacts are silver plated. A cadmium silver alloy is used for plating the fixed contact and moving contact. This is because the silver is a malleable, and when the moving contact presses firmly over the fixed contact, the silver gets flattened out and the area of contact between the fixed contact and the moving electrode is minimized. That gives minimum ohm resistance of the circuit breaker. Now, when the lock is removed and the moving contact quickly moves away from the fixed contact, a arc strikes. And due to this arc, the current does not become suddenly zero till this arc is extinguished. So the entire theory of circuit breaker is how to quench this arc as quickly as possible so that damage is minimized. So we will study how to quench the arc. As the current is AC, the arc is not continuous. When current is non-zero, the arc is there, and when the current passes through natural zero, in that case the arc extinguishes. So in every half cycle, the arc will extinguish 2 times, and a full cycle, the arc will extinguish 4 times. That is, after every 10 milliseconds, the arc will extinguish. So the arc extinguishes by itself, and when the current again rises in the other direction, the arc is re-established, and it again continues for 10 milliseconds, and again meets another zero, it stops, and so on. So if we make no other attempt but simply make efforts to prevent the arc from re-striking after it has already been extinguished at natural current zero, our job is done. So again, briefly we can say the circuit breaker theory is again concentrated only to prevent the restriking of the arc when it has already become zero at natural current zero. Now when the arc is extinguished at current zero, we have a situation like this. And when there is no contact between fixed and moving electrodes, then the voltage across these two will rise. So there will be a voltage. When there is no arc, there will be a voltage. Now there are two important components of this voltage. One component is power frequency. Other component is transient high frequency component. As before opening the circuit breaker, the current and voltages were not in phase. During fault conditions, the power factor is almost 0 lagging, and voltage is leading the current by approximately 90 degree. That is, the power frequency component will be such that when the current naturally becomes 0 and the arc extinguishes by itself, that time the power frequency voltage will be almost at the peak value. And this voltage will rise from 0 to the peak value within a very short period and appear across the contacts. Another is, as the arc extinguishes, the voltage suddenly changes from 0 to a maximum value, and due to the sudden change of voltage, there will be oscillations between the system inductance and the system capacitance. So, if this is a source, this is a circuit breaker, so source, a circuit breaker, and there is a fault over here. L is the inductance in the circuit, resistance is very small in the circuit compared to inductance. This is a stray capacitance, and these are again stray capacitances up to the fault point. At natural current 0, this arc vanishes. The arc at the fault also vanishes for a short period at natural current 0, and these capacitances will like to charge to the maximum voltage of the source, and therefore oscillation will be established between this inductance and these capacitances. Frequency of these oscillations this will be the frequency of the oscillations. As inductance and capacitances are extremely low, the frequency is very high. It is of the order of several tens of kilohertz. So, that high frequency voltage will also appear, and the power frequency voltage will also appear. Now, whether due to this voltages will the arc restrike or will it not restrike? We should create such situations so that the arc does not restrike. Now, there are two theories to explain that whether the arc will strike or the arc will not restrike. The contacts are open, and in all the circuit breakers, we make efforts to cool the arc path. This path we will try to cool it by forcing more media in between the contacts. Also, we will generate mechanical forces to mechanically move away the ions due to previous discharge. Now, The rate of rise of restriking voltage theory says that the arc will restrike if the rate of rise of voltage across the contact is higher than the rate of recovery of the dielectric. That is, if the dielectric recovers very fast and the rate of rise of voltage across the contact just after current zero is not high enough, in that case the arc will not restrike and circuit breaker will successfully open. And vice versa, if the rate of rise of restriking voltage is high and rate of rise of dielectric strength is not that high, in that case the arc will restrike. So efforts should be made to reduce the rate of rise of restriking voltage so that this may not happen like this. Other theory is the heat valence theory. The heat valence theory says that when the contacts are separated, then some ions are in the contact, so there is a resistance due to previous ions present in the arc path. And if the voltage across the contact at any instant V, then heat generated in the contact region is V square upon R. So this resistance is R and heat generated will be V square upon R. This arc is resistance between the contacts due to ions present due to current flowing before current zero. So V square upon R is the heat generated in the contact region, and there is a certain rate at which we are removing the heat by conduction in the media, by convection in the media, by mechanical force developed to remove the ions away from it, and recombination of ions also, which may occur naturally. So the theory says if the rate of generation of heat due to V square by R is higher than the rate at which the heat is removed from the contacts, the arc will restrike. And if the rate of heat removal is slow and rate of heat generation due to V square by R losses is high, in that case the arc will restrike once again. So broadly both the theories are similar, that this also depends upon the post arc voltage and that theory also depends upon post arc voltage. But mathematically if we calculate and apply it to a particular circuit breakers, then in some circuit breakers the heat balance theory gives better results, and some circuits the rate of rise of restriking voltage theory gives a better results. We can use the heat balance theory in oil circuit breakers which are comparatively slow, and in air blast circuit breakers the media is air, and there we can get better results by applying the rate of rise of restriking voltage theory. But very enthusiastic efforts to blast the media between the contacts at a high rate is also harmful. So what is done, that if between contacts we can force the oil to blow out the arc. Or we can force the oil here to flow like this. Efforts will be to remove the ions present in the arc path. This is called a cross blast. And this is called an axial blast. In axial blast, the quenching medium or the cooling medium is passed along the axis of the electrodes, and in cross blast, the cooling medium is forced perpendicular to the arc so as to blow out the arc. Now we understand that in the cross blast, the arc may be blown out very quickly. And in the axial blast, the arc force on the arc to blow out is not as strong as in the oil blast. Now we will try to see that if the arc is blown out very quickly, that is before the natural current 0, then there is a phenomena called chopping. Chopping is a phenomena to blow out the arc before the occurrence of natural current 0. Now in the circuit, and arc, the current is flowing at some extent is equal to IA. And if the arc is blown out, say somewhere here itself, where the current IA has not reached natural current 0, but before that we are blowing out from here. There is an inductance, and the effect will be that a high voltage will get induced equal to what we can write down. So capital V is the maximum transient voltages. Cos of 1 by root LC into T is the wave of high frequency transients. Then at any instant T, the voltage induced here, or that is same as between these 2 points, will be given by this expression. So this is a very high voltage so produced. So at this instant, the voltage was 0. and now the voltage suddenly rises to a very high value like this, and due to this high voltage, this arc again restrikes. It was broken before natural current 0. Now it will restrike before natural current 0. And when it restrikes, the voltage again goes down 0. Then as this blast is going on, a comparatively weaker arc now because of lower current, that will definitely be break the gap, and it will restrike the arc, and again the voltage will become 0. Again there is a and so on till the natural current 0 comes, and when the natural current 0 comes, then it will not restrike again because voltage induced will be 0 at natural current 0. So here the current chopping phenomena will give rise to a multiple pulses of high voltages. A single high voltage pulse can be withstood by an insulator, but if multiple high voltage pulses are applied to an insulator of the same voltage, the insulator may fail. So supporting porcelain insulators of the circuit breaker may fail due to this current chopping phenomena. So this gives an additional restraint in the design of circuit breaker, that we should apply the blast of oil or air or whatever it is, so that the arc may not restrike after natural current 0. But it should not be so strong that it may lead to current chopping. So current chopping is also harmful, and not allowing the arc to strike, that will give rise to a repeated arcing, and therefore delaying the opening of the circuit breaker. Due to this reason, some circuit breakers are designed in such a manner that the arc is blown out by axial or radial, or a combination of axial and radial, by the force generated by the heat produced by the arc. So if the heat produced by arc is more, then more force to blow out the arc is produced, and vice versa. So that for higher fault currents, less blowing out force is produced, so that current chopping may not occur, but as the current is low, lower blast will do to quench it at natural current 0, and vice versa. Whereas in certain circuit breakers, like in air blast circuit breakers, this force to blow out the arc is constant force, whether the current is low or current is high. In both the cases, it is same force, and there is a greater possibility of occurrence of arc. Now another thing to weaken the arc is to go by resistance switching. Now, if you put a resistance here, then this resistance will come in series with the LC circuit, and frequency of oscillation is modified. The high frequency transient oscillation frequency is modified, and it is given by this relation. R is also called a damping resistance. If R is low, the second term will be higher. So there will be oscillations as long as the second term is lower than the first term. And if R is low enough and is greater than or equal to 1 upon LC, no oscillations. So by properly choosing the value of R, it is possible to totally stop the high frequency transient oscillations. And high frequency transient oscillation are the bigger culprit to restrike the arc. Because when the voltage is varying very quickly at high frequency, the rate of rise becomes very high as compared to 50 cycle voltage. The rate of rise is very low. So power frequency rise of voltage is not much responsible for restriking of the arc after the natural current zero. But the bigger culprit is the high frequency voltage, whose rate of rise is very high. And if this high frequency voltage is totally quenched by properly choosing the switching resistance, then the possibility of restriking becomes extremely low. But this current may stop, but this current continues to flow, and we have to put a smaller switch in series with this to produce a weak arc due to this resistance switching. So that is, switching is done in two steps. First we stop the main arc, and then we stop the auxiliary arc. Or in bulk coil circuit breaker, a tank filled with mineral oil, that is the transformer oil, is taken, And fixed and moving contacts So, fixed and moving contacts of all the three phases are dipped in the oil tank. Sufficient clearance is kept between the contacts of different phases and between the contacts and the wall of the tank. Then the lower contacts, that is the moving contact, are lowered down, the arc stucks. The arc is quenched by the heat taken away by the oil due to conduction process as well as due to conduction process, the convection process. So only that is the cooling. Cooling is very mild and it can be used only for lower voltages and lower current. So oil is doing both the functions of insulating the different phases and earth and also for cooling the arc. Due to large amount of oil required, the circuit breaker is costly as the cost of oil is high, and at the same time this is a slow circuit breaker, means the arc restrikes several times and then only it is quenched. So this is a comparatively slow circuit breaker. But the advantage is that products of arc, that is the carbon particles and other burnt oil, gases which are produced, are of low percentage compared to the bulk of oil. So the impurities will disseminate in the oil and the percentage wise the quality of the oil will not be much deteriorated, and therefore it can be used where the faults are occurring very frequently, that is like that in the rural lines where faults are more frequent. This can handle that type of situation. There is a fire hazard that in case the oil leaks from the tank, in that case there can be a fire and lot of oil is present here, so fire could be very serious. So this is a suitable circuit breaker for low voltage, low current application. For a higher voltage and higher current applications, we use a minimum oil circuit breakers. That is, we do not use so much oil. So in minimum oil circuit breakers, oil is used only for quenching the arc and oil is not used for insulation. So all the three phases are provided in three separate insulators. So this is an insulator for the R phase, and there is a separate insulator for Y phase and separate insulator for B phase. Now each is a hollow porcelain insulator, and inside the hollow porcelain insulator we have a fixed contact and a moving contact. And this portion is filled with oil, like this, here also like this. So this is for the R phase, this is for Y phase, and this is for B phase. So these contacts are insulated from earth due to insulation porcelain present here, and between these two the insulation is provided by the porcelain provided on both these. So the oil which was required for insulation purposes, that is avoided. Now when the contacts separate, the arc is struck between these 2 points, and only this much oil will participate in the arc quenching. As this oil is insufficient, we put arc chutes. So arc chute is a small cylinder kept around the arc, and there are windows cut on the periphery of the arc chutes, and also the distance here, it is not a tight fit, it is a loose fit. So that when the arc strikes, the oil can flow like this, and due to windows present on the periphery, the oil will also move so oil moves outside these chutes axially as well as radially, and therefore remaining oil in the bushing is also utilized for arc quenching purposes. A minimum oil circuit breakers requires only 10% oil. As compared to a bulk oil circuit breaker. So there is a great saving in the amount of oil, but in each break some oil gets evaporated, some oil gets burnt due to arc, and frequently that after 4 or 5 breaks we may have to check the oil level and we may have to top up the oil. Minimum oil breakers have been designed for voltages up to 1000 kV and for currents up to 50 kiloamperes. And this is the most popular circuit breaker in most of the substations, because this can satisfy most of the requirements. These are again low duty circuit breakers, and they use only air. So this is the fixed and moving contacts, and these are metallic horns. In between there are so many metallic plates insulated from each other. When the arc strikes here, due to heat of the arc takes a convex shape, and then it is blown up, and it's blown up into number of arcs occurring between the plates. So there is a lot of cooling of the arc, and air is blowing in this direction, air. The arc is ultimately quenched. This is a slow circuit breaker, and there is no possibility of chopping here. It takes long time to blow out and suitable for low duty, that is for lower currents. if this is to be used, that is for load breaking purposes, this is quite a suitable circuit breaker. In air blast circuit breakers, we make use of a separate air compressor and a high pressure air blast is thrown over the fixed and moving contacts. Due to high pressure air blown over the contact, the arc is blown out. This is a very strong circuit breaker. The air is thrown only for a very short duration, just for less than a second, and the arc is blown out. There is a violent sound created due to operation of the circuit breaker because of high pressure air injected on it. This is also a very popular circuit breaker for 220 kV and above. But we have to maintain a compressed air separately for this purpose. So this is the disadvantage. There is no oil in it, therefore there is no risk of fire, etc. And also a popular type of circuit breaker. The amount of air used is very little, and therefore once we charge the compressor fully, then we can operate it several times. Now in the vacuum type, we make use of vacuum at a pressure of 10 to the power minus 6 to 10 to the power minus 8 bars. 1 bar is equal to 1 atmospheric pressure. So 10 to the power minus 6 of the atmospheric pressure. So a hard vacuum is maintained and the contacts are separated inside vacuum. And the arc can sustain in the vacuum only in the vapors evaporated by the electrode material. The electrode material itself evaporates due to temperature of the arc and it generates a little pressure. When pressure is very low, distance between different molecules are high and mean free path becomes longer. If mean free path is much longer than the separation between the electrodes, then arc cannot survive. So this is a very powerful but a very miniature size circuit breaker, becoming popular nowadays because of the availability of good material. SF6 is an inert gas, and this gas is maintained at a pressure of 3 kilogram per centimeter square and is a very good arc quenching properties, and this type of circuit breaker is also getting popularity and it's already in use as many installations. Thank you.